Schrödinger's cat is one of the strangest ideas in all of physics. A cat in a box that is somehow dead and alive at the same time sounds absurd, and that's exactly the point. Schrödinger invented this imaginary cat not to explain quantum physics, but to show how confusing our interpretation of it had become. In this video, we're going to break down what Schrödinger's cat really means, why it became so famous, and what it actually teaches us about the boundary between the quantum world and the world we experience every day. Schrödinger's cat is one of the most famous ideas in all of science. A cat inside a box that is somehow both dead and alive at the same time. It sounds like science fiction, or a joke, or a meme that escaped the internet. But behind this strange story is one of the deepest problems in physics, the problem of how we understand reality itself. And the surprising thing is this Schrödinger never meant for the cat to be mysterious. He invented it to show how strange quantum physics had become, and why something about our understanding wasn't quite right. So let's break down the entire story, simply, clearly, and without jargon, and finally understand what Schrödinger's cat really means. To understand the cat, we first need to understand the world. It came from the world of quantum mechanics. At the smallest scales of nature, far smaller than atoms, particles behave in ways that make no sense in everyday life. Electrons don't sit in one place. Photons don't follow a single path. Particles don't choose a single state until we measure them. Instead, they exist in what physicists call superposition, a state where multiple possibilities overlap at the same time. A particle can be here and there, spin up and spin down, detected and not detected, all at once. It's not magic, it's just how the math works. For small particles, superposition is normal. But this raises a huge question. If tiny particles can be in multiple states at once, why don't we ever see big objects like chairs or trees or cats doing the same? That question bothered Erwin Schrödinger. And in 1935, he came up with a thought experiment that would become legendary. Let's imagine the setup in simple terms. You take a cat and put it inside a sealed box. Inside the box is a tiny bit of radioactive material, something so small that after 1 hour, it has a 50% chance of decaying and a 50% chance of not decaying. If the atom decays, it triggers a mechanism that releases poison and kills the cat. If it doesn't decay, nothing happens, and the cat stays alive. This is important. Radioactivity at the atomic level follows quantum rules. It behaves in superposition until measured. So after 1 hour, the atom is in a state of both decayed and not decayed. And if the atom is in both states, then the mechanism is in both states. And the cat, according to the logic of quantum mechanics, is both alive and dead. Not metaphorically, not symbolically. Literally described by the math as a superposition of a live cat and dead cat. But here's the twist: Schrödinger didn't propose this to show how cool quantum physics is. He proposed it to show how absurd the interpretation had become. He was essentially saying, if your theory leads to cats being alive and dead at the same time, maybe the theory needs clarification. Schrödinger was criticizing quantum mechanics, not celebrating it. But to understand why the cat matters, we have to look deeper into the idea of superposition. For a particle, superposition means this: the particle has not chosen a single definitive state until it is measured. Before measurement, it behaves as if all possible states are true. Think of it like this. Instead of picking a single option from a list, nature keeps the whole list active until an observation forces a choice. This is why quantum mechanics is so weird. It says the act of measuring doesn't just reveal reality, it helps create it. The cat thought experiment pushes that weirdness to the limit by linking a tiny quantum event to a big classical creature. But then Schrödinger asked the crucial question: when does the collapse happen? When does the system go from both states to one state? When the atom is observed, when the mechanism triggers, when the box is opened, when a human sees it, or at some earlier moment. Quantum mechanics didn't give a clear answer. The Copenhagen interpretation, the most common view at the time, argued that superposition is real until measurement. But Schrödinger pointed out that if you apply that idea to everyday objects, you get absurd results like cats in 2 states at once. This exposed a major gap in the theory. Quantum rules didn't clearly explain how the tiny world transitions into the large world we experience. Physicists needed a way to explain why superposition exists for particles, but not for people or cats or tables. One of the most important ideas that came later is something called decoherence, which we're going to explain without equations. Decoherence says that quantum superposition only survives when a system is perfectly isolated from its environment. The moment it interacts with anything, light air molecules, heat vibrations, anything at all, the delicate superposition collapses into a definite state. Tiny particles can stay isolated. Big objects cannot. A single atom can avoid interaction for long periods. A cat made of trillions of atoms constantly interacts with the environment. It breathes, moves, exchanges, heat touches the box. All of these interactions destroy superposition instantly. So the cat is never really in a quantum overlap of alive and dead. The superposition collapses long before the states can scale up to something as big as a cat. This is why we don't see everyday objects in superposition. The world is constantly measuring them through interaction. But even with decoherence, the deeper philosophical question remains. What does superposition mean? What does the math of quantum physics say about reality itself? One bold answer is the many worlds interpretation. According to this view, when a quantum event has multiple possible outcomes, the universe doesn't pick one. It splits. In one branch of the universe, the atom decays. In another branch, it doesn't. In one branch, the cat dies. In another branch, it lives. There is no collapse, only branching. This interpretation is popular because it solves many mathematical issues, but it introduces massive philosophical ones. How many worlds are there? What counts as a branching event? Can branches recombine? It's still debated today. There are other interpretations too: pilot wave theory, objective, collapse theories, relational quantum mechanics. But Schrödinger's cat remains the clearest way to show how differently these interpretations imagine reality. So, what does the cat really teach us? First, it teaches us that the quantum world and our everyday world are connected, but not in a straightforward way. The rules for tiny particles don't simply scale up to living creatures. Second, it teaches us that observation is not just a human act. It can be any interaction with the environment. Third, it teaches us that our intuition about reality breaks down at small scales. And finally, it teaches us this profound insight. Schrödinger's cat isn't about a cat. It's about us and the limits of how humans understand nature. Schrödinger didn't want us to picture a magical cat flickering between two states. He wanted us to see how incomplete our models were. He wanted to warn us that the universe is stranger than we imagine, and stranger than we're comfortable with. The cat in the box was never alive and dead. It was a spotlight shining onto one of the deepest puzzles in physics. How does reality decide what is real? And that puzzle remains open. The universe still hasn't revealed its final answer. But one thing is certain: after Schrödinger's cat, we can never look at the boundary between the quantum world and everyday life the same way again. If this explanation made Schrödinger's cat finally make sense, then you've just seen why it still shapes our understanding of quantum physics nearly a century later. The cat isn't a paradox about life or death. It's a reminder that the universe at small scales doesn't follow our intuition. If you want more videos that turn confusing scientific ideas into simple, clear stories, make sure to subscribe, leave a like, and tell me what topic you want explained next. Thanks for watching. Plain Explain, where even the weirdest ideas become understandable.